Good morning.
How are you today?
Doing all right. How about you?
Good. Down everything that I'm doing. I don't know if your camera makes a difference or not, or when I turn mine off, maybe you're forced to turn, yours disappears. But anyway, let's get back to this. Okay, so if du equals dx, well, dv, if I divide both sides by dx, I got dv dx equals sine x. Therefore, v must equal negative cosine x.
Right. Yep.
So now I can set up my equation. Well, what's u? U is x. What's v? V is negative cosine x. What's the integral of v? That's a negative cosine x. And then du is dx. So I've turned it into something that I can't integrate into something that I can now easily integrate. So the final answer is, and then the integral of negative cosine is negative sine, and then a negative times a negative becomes a plus c if it's an indefinite integral.
Okay.
Okay? Now, these can get particularly tricky if we were to have started with x squared. By the time we get to this step here, we're going to have narrowed it down to an integral of x cosine x.
Right. Yeah.
Which means we would need to do another iteration.
Yep.
When you're integrating by parts, if this was started out x to the sixth, you're going to have to do it 5 times to narrow it down. In other words, the second iteration would drop that 6 to a 5, the next one would to a 4, and eventually you get it all the way down to where your last integral here is doable. But integration by parts is an iterative process, and in fact there's a tabular method that they teach. Have you been taught that?
No.
Okay, I won't go into it. For now, we can just do some examples, and I have some other examples. If you don't have any, let me find some in my book, and we can go through another example of integration by parts. So there's some really cool things that happen when you integrate by parts.
I have one here.
Okay.
It's the integral of x times cosine of 5x dx.
This is going to be fairly straightforward, pretty much like the last one. So
okay.
Based on Lippitt, what is u going to be?
X.
Which makes dv
Cosine of 5x.
dx. In other words, dv is everything that isn't u.
Yep.
You can't have a differential equation with just one differential in it. It doesn't make sense mathematically to say dv is equal to cosine of 5x. You always need that other differential in there. So differentiating the left, du is equal to what?
X squared over. Oh. Yeah, just dx.
Okay. That's okay. And then v is equal to what?
Negative sine.
Actually, we're integrating this, so it's going to be positive sine of 5x divided by 5. Whenever you take the integral of cosine of ax. It's sine of ax divided by a.
Right, yeah.
If you take the derivative of this, you get cosine of 5x.
Right, okay.
Okay? So now our answer is what? It's uv minus the integral of v du. So tell me what that would be.
Okay. It's x times sine 5x over 5. Minus dx, so sine 5x over 5. Yeah. Dx.
Okay? And the hardest thing with integration by parts, believe it or not, is keeping track of your negative signs. Because especially if there are multiple iterations, you end up with an equation that has about 6 negative signs in it. And if you don't have your parentheses just right, you're going to be off on a sign at somewhere. So this is the integral of sine is what? What's the integral of sine 5x over 5?
Can you move the 1/5 out?
You can, although I don't find that particularly useful. In other words, you can take the antiderivative of sine of 5x the same way we took the antiderivative of cosine of 5x. It's going to become negative cosine of 5x divided by 5, but now it's divided by 25 because 5 times 5 is 25.
Okay.
So again, if I were to take the derivative of this, I would get sine 5x over 5.
Okay.
Okay? So this all becomes a plus, and that's your answer. But that's pretty much the same as the one we did. I'd like to show you a different one to illustrate, well, let's see, integration by parts. Well, we have to, I'm going to have to look it up in the table of contents.
Would the integral of x tan squared of that be a good one?
No, that's not going to be, well, I don't know. I'd have to look at that one, but I'm looking for a particular problem. Here, I'll give it to you in a second here. No wonder. I was way, they really jumped chapters in my book. There's about 100 pages between integration by substitution and integration by parts. Now something particularly cool goes on. If I can find this one. Hold on. Okay, here's a good one. Sorry. There's a process that you never do in anything else. I can't believe I can't. Maybe it's the e to the x. Yeah, x. Excuse me a minute. No, I can't find it. So, oh, maybe this is it. Yeah. Okay. Here's a particularly tricky one. This is a little tricky because this is where you want to pick dv instead of u. In other words, if I have secant cubed of x, it's not clear what u is going to be, as all I have is trig functions there. So one of the suggestions in this book I have is the most complicated part of the integrand that can be easily integrated. There's the key, is what can be easily integrated? Well, secant squared is easily integrated because the antiderivative of secant squared is tangent. So we're going to let u equal secant x and dv equal secant squared x dx. And the logic behind this is, like I said, a little tricky, but it's going to demonstrate the point that I really want to demonstrate to you. So let's proceed here. What is du? Actually, the derivative of secant is secant tangent.
Okay.
It's one of those harder ones to remember for sure. dx. Okay, and v is the integral of that, which is tan x. So now when we put it together, uv is secant x tan x minus the integral of tan x du, which is secant x tan x dx. Did you get that part?
Yep.
Okay, that's secant squared tan x. Now I can substitute for tan x secant squared minus 1. So this becomes secant squared minus 1 times secant x dx. Okay, I'm getting to the good part. So now we have, this is all equal to secant x tan x minus the integral of secant cubed x dx plus the integral of secant x dx. And all of this is supposed to be equal to the secant cubed of x dx. Well, I know how to take the integral of secant x dx. That is natural log of secant x plus tan x. So I've got on the left side of the equation, the integral of secant cubed x dx is equal to that plus that minus that. So what do you figure my next step is going to be? Here's what I've got. And this is what's cool that you don't see anywhere else. Let me erase this. Secant plus tangent x. Give myself a little more room. Same thing we started with, right? So it might look like we've run into a brick wall. What do you suppose I can do next? I can add the integral of secant cubed of x dx to both sides. In other words, I can take this term over here and move it to the other side of the equation, making two of them. Put a 2 right there, erase this term. Now I have my answer. So all I have to do is divide both sides by 2. There's what the integral of secant cubed is equal to. I could have picked a simpler example, but the concept is basically the following. If I'm solving for x, and I get that x is equal to a plus b minus x, well, I'm going to add x to both sides. So now I got 2x equals a plus b. So x equals a plus b divided by 2. And that's, in essence, what we're doing when we have integration by parts. Only instead of x, this left side is the integral of some function, and this was the integral of that same function. So it's perfectly legitimate to add an integral to both sides.
I do have one question.
Okay.
How did you split up
The secant cubed in the first place?
down a little bit, I think.
Okay, probably right here, where I had tangent squared x secant x. I used the trig Pythagorean identity that tangent squared is equal to secant squared minus 1.
I got that, but then where did you get the two integrals there? Right.
By distributing this, and I end up with secant cubed minus secant. Now, it turned into a plus because all of this was in parentheses, and it was all being subtracted. So when I distributed this secant times this, I got a minus secant cubed x, an integral of that. But then the second integral becomes plus because I have a minus and a minus. And now I know how to integrate that. That is that right there. So the only unknown left on the right side of the equation is the integral of secant cubed x dx, which is what we're trying to solve for in the first place. All right, that to me is one of the more important principles of integration by parts. Let's do a different one. How about x squared natural log x?
Okay.
Based on Lipit, what would I let u equal to? And what would I let dv equal to?
U would be x squared.
Remember Lipit? The top L stands for log, which means that if there is a log in one of these functions that we're trying to integrate, then that's what you should let u equal to.
Okay. So it's the first, I guess, letter in Lipit that comes out.
Yes, you go by that order. In other words, you let an exponential be u over a trig function, or you let a polynomial be u over an exponential. The top of the list is log, so you always let u equal to the log part of the function, which makes the rest of it x squared dx. Okay, what's du? What's du dx?
Over x.
Okay, so that's 1 over x, so I can put my dx up there. Get rid of it there. And then what is v?
X cubed over 3.
So now what is uv minus the integral of v du?
Ln x minus x cubed over 3.
Yeah, I usually put the polynomial in front just to avoid misreading the argument of the log. So that's uv. What's the rest of it?
1 over x times x cubed over 3 dx.
Like that? Okay. And now we have something we can integrate. So our final answer is what's the integral of this?
X to the 1.
Okay, first of all, let's cancel this x with that exponent. So now it's x squared over 3.
Cubed over 9.
Yeah, x cubed over 9. Let's do one more that involves inverse trig function. And
I have one here.
okay, go ahead.
The integral of cosine for cosine.
Didn't quite hear that.
It's integral of inverse cosine x dx.
That's funny. The one I was going to give you was the integral of the inverse sine of x dx. That's freaky. Okay. So what should we let u equal?
Inverse cosine.
Yeah, that's near the top of the list. It's right below L. So, and we know how to differentiate that. So dv is what?
Dx.
So what's du? The inverse cosine. That's one of those that is, Yeah, just a second. I've got a table here. That's 1 over square root of 1 minus u squared, only it's negative. That's basically the relationship that you want to remember, is that the derivative of the inverse sine is the same as the derivative of the inverse cosine, only it's negative of it.
Right.
Okay, and what is V equal to? So UV is inverse cosine of x times x minus the integral of x du. Well, du is this whole thing. So it's minus 1 over 1 minus x squared. This was supposed to be an x, excuse me, dx. In other words, this whole thing is du. In parentheses.
Yep.
Okay. And now integrating that. So we've got, oh, that integrates. This is a good problem. Okay, what is the integral of, we're going to take that minus sign outside and turn this into a plus so that it's x over, excuse me, there's a radical sign there. Now what can we use to integrate this?
Now we can use sine.
And some people would say that you'd have to use substitution. Other people would say, well, you could just use the power rule. But just so that you understand the power rule when used in this sequence, let's use substitution just to make everything perfectly clear. Now, you got to be a little careful here because we're integrating by parts, so we already have a u and a v. So let's not reuse u to mean something else. Let's pick a different letter. Let's let r equal to 1 minus x squared. Okay, so what's dr dx?
Just negative 2x.
Which means dr is negative 2x dx. So I'm going to put this integral as an integral of r, and it would be x over r to the 1/2, and then dx is equal to dr divided by minus 2x. That's what dx is equal to, and that's what I need to put here is something that has a dr in it. And the beauty is now the x's cancel, so I'm left with an integral that I can do. The integral of 1r to the negative 1/2, and I'm going to take this negative 2 outside the integral like that, dr. Okay, is there anything you didn't understand in me getting to that step there?
No.
Okay. What's that?
It's just that I don't know if I'm wishing myself to do that. But I understand it. Yeah.
Okay. And so when we integrate this, this becomes r to the plus 1/2 divided by plus 1/2 or multiplied by 2. So this integral becomes r to the 1/2 times 2 times this minus 1/2. So that is our integral for r. And we still have the uv part of it, x inverse cosine of x. and it's now become a negative again. And now when we go back and substitute this for r, we get negative the square root of 1 minus x squared to the 1/2. No, r was equal to 1 minus x squared, not the square root of it. So it's 1 minus x squared to the 1/2. And that's our answer. Yeah, and the answer in my book is exactly the same, only with a different sign. In other words, if we were integrating the inverse sine instead of the inverse cosine, it would change that to a plus, and that's the only difference. And then, of course, well, in my particular problem, we were going from 0 to 1, so we now have to evaluate this whole thing from 0 to 1. And that, of course, also involves a lot of negative signs. Notice we're going to substitute 1, and then we're going to go back and substitute 0. And so by the time you get an answer, you're going to have kept track of a lot of negatives. Okay.
So that's the only difference for a definite. You just have to evaluate at the very end.
Well, there's two ways to do it. First of all, I had a 0 to 1 in my problem. So if I go all the way back to the beginning, my problem was to evaluate it from 0 to 1. Well, notice that when I used substitution and turned it into r, I can no longer evaluate this from 0 to 1. It's not the same function. In other words, you can do it two ways. The easiest way is to resubstitute for r and then evaluate it at your original limits of integration. If you want to evaluate this thing directly, then I have to find new limits of integration. When x goes from 0 to 1, what does r do? Well, r goes from 1 to 0. So if I wanted to actually evaluate this, I would have to go from 1 to 0 instead of 0 to 1. In other words, you figure out what r goes to when x goes from 0 to 1, r goes from 1 to 0. But rather than changing your limits of integration, and I've never really seen a problem where you have to evaluate it at the new limits of integration, it's always simplest to go back and resubstitute for r and then evaluate it at your original limits of integration. Hopefully that answered your question.
So you could just, so for the final answer, you could just leave it as the limits are, the bounds are.
Well, yeah. In other words, you don't have to resubstitute for r here. You can actually do this integration and evaluate it from 1 to 0. And that'll give you the same number as if you substitute back in and evaluate it from 0 to 1. So you can do it either way. To me, it seems like an unnecessary step to figure out the new limits of integration if we're integrating a function of r. Why take that step? We already know the old limits of integration, and it's not that hard to resubstitute 1 minus x squared for r. Okay. Why don't you give me your work problem, if you have a good one. And we'll take a look at it today, and if we can solve it today, fine. If not, we'll finish it at our next session, which is Friday morning.
Yep.
Do you have a test between now and Friday?
I have a test on Friday at 11.
Okay. Good.
So the work problem is,
Is it a rope and bucket with water in it by chance?
no, it's not, but we could do one like that.
Okay. I happen to have a nice one like that.
Okay.
Let me see if I can find it.
I do have one here.
Yeah, it might be easier if we use mine, just because calculus applications, it's got to be in this chapter. 12. Hopefully we'll have time to do both. All right.
Are you also still familiar with the ones where you're training a pool or training an aquarium or something like that?
I've looked at all of those. Some of these work problems can be a little difficult to set up and analyze. That's why I kind of would like you to give it to me. If you have any special ones, yeah, I do have one. The work done pumping from a conical tank,
Okay.
where you have to divide the fluid into slices of fluid.
Right. Yeah.
In other words, anything where there's a variable as you empty it, the work changes. It's a variable workload. But the bucket one illustrates a pretty good principle. It's probably worth going over the bucket problem.
Okay.
I've got a leaky bucket that weighs 22 newtons. It is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 4 newtons per meter. That's the rope's density. The bucket starts with 70 newtons of water in it, but it leaks at a constant rate, and it just finishes draining as the bucket reaches the top. Find the amount of work done lifting the bucket alone, lifting the water alone, lifting the rope alone, lifting the bucket, water, and rope together. Okay, the bucket alone. This is easy because the bucket's weight is constant, so it doesn't really require calculus. To lift 22 newtons, a 20-meter interval, that's 400. The amount of work to lift the bucket is its weight, 22 newtons, times its distance, 20 meters, 440 newton meters, and those are called joules. The water alone. Now, one of the key things said that the water is leaking steadily. The water alone weighs 70 newtons at the beginning of the lift, but then it weighs 0 newtons at the end of the lift because it's exactly leaked out the whole way. So if you were to plot the weight of the water versus the distance, that being 20 meters, this being 70 newtons, it's a linear curve downward, which makes the calculus easier. We don't have a variable rate of leakage. We have a constant rate of leakage. So the force needed to lift the water is equal to the water's weight, which decreases from 70 to 0. When the bucket is X meters off the ground, the water weighs, the force of the water, based on that graph, is 70 times 20 minus X over 20. This is the original weight of the water, the 70, and this is the proportion left at elevation X. In other words, when we're 10 feet off the ground, we have 1/2 the water left. When we're 20 feet off the ground, we have 0 water left. So this expression gives you the weight of the water as a function of the height off the ground. And this simplifies to 70 minus 3.5 x newtons. And the work done lifting the water is the force. This is basically an integral as net change problem. So the work done lifting a force, f of x, dx, from A to B, or in this case from 0 to 20, is going to be from 0 to 20 of this function, the force function, because we know work is force times distance. So the force function is 70 minus 3.5x dx. And that's an easy one to integrate. What's the antiderivative of this integral here?
70x minus
just always just add 1 to the power and divide by the new exponent. Okay? And then if I evaluate this expression going from 0 to 20, I get 700 joules. So that's the amount of work lifting the water. Okay, now let's talk about the rope alone. Well, the force needed to lift the rope is also variable, and it starts out as the density of the rope was given to us at 0.4 per meter. So the total weight of the rope at the beginning of the lift is 20 times that. So the weight of the rope begins at 8 newtons. But that's when the bucket's on the ground, and it ends at 0 newtons, because by the time you've lifted the rope all the way to the top, the remaining part of the rope is 0. Okay, and as with the leaky bucket, the rate of decrease is constant. When you've lifted up half the rope, only half the weight remains. When you've lifted up 3/4 of the rope, only 1/4 of the weight remains. So it's a linear change. Okay, so the force of the rope is equal to its density times 20 minus x newtons. In other words, when x is 0, it's equal to 8 newtons. When x is 20, it's equal to 0 newtons. So the rope alone is going to be the integral from 0 to 20 of this function, 0.4 times 20 minus x dx. And if we do that math, we get 80 joules. So for the bucket, the water, and the rope together, the bucket was 440. That was easy. The leaky water was 700 and the rope was 80. So all three total required 1,220 joules of work to lift.
Okay.
Now, if one of these functions that was a variable force, in other words, both the rope and the water was a variable force, as you lifted it, the force changed. In both of these cases, it was linear, but that doesn't really matter. It doesn't have to be linear. It could be parabolic or exponential. In other words, maybe most of the water leaks out early and it doesn't follow a consistent. Then all that means is f of x is going to be a nonlinear function instead of what we had, which was a linear function. Won't matter. You can define f of x as whatever you want. Now, for the rope, f of x is always going to be linear, assuming it's a consistent rope. But for the leaky water, that might leak at a different rate. I guess it would always kind of leak at a constant rate. But you can imagine work problems where this f of x function is not linear. It's maybe quadratic or cubic or something like that. Okay. Do you have a problem that is pumping fluid out of a tank that you'd like to give me?
Yeah.
Okay. Why don't we start it? I doubt that we'll be able to finish it today, but we might. We'll try to get through it.
Okay. So an aquarium is 2 meters long, 1 meter wide, 1 meter deep.
Okay.
Full of water.
It's full of water, okay.
And then just find where you pump half of the water out.
Okay.
And
We have a density of water.
it's 1,000 per meter.
4,000 pounds per cubic meter.
They gave it in 1,000 kilograms.
Okay. So did you say 4,000?
No, I said
1,000. Okay. I was going to say, because water is the standard, and especially if you're in the metric system. Okay. So this looks fairly straightforward. Let's see if we can draw a picture here somewhat. I'm horrible at 3D images, but the water line's at the top, and we want to drain it to here. So we have to pump that water up a certain height. Well, this height is 1 meter, the full height of the side. So we actually have to pump the water from 1/2 meter to 0, or from 0 to 1/2. So whatever our work function is going to be, we're going to pump it from 0 meters to 1/2 meter. Right? Okay. What's the force of that water?
So why is it that you pump it up?
Well, there wouldn't be any work required in pumping it down.
Okay.
If I put a hole in the bottom of the aquarium, I can drain half that water out without any work at all. But so for this to be even a work problem, we're going to pump the water up over the ledge. But of course, the first slab of water that we have to get rid of is the nearest to the top, so we don't have to pump that the full distance. We only have to pump that a marginal distance. This is where work problems get tricky, because you can have a slab of work or you can have a slab of water that you're pumping. What we're going to imagine is that the water is going to be partitioned into thin slabs by planes perpendicular to the height. In other words, this is the front of my aquarium. This is the back side. So if I want to picture rectangular slabs of water that have thickness dx, and I'm going to picture pumping them out of the aquarium. And I'm going to pump from varying distances. The initial slab that I have to pump out is the top slab, which doesn't have to go far. And the very last slab of water will be at the 1/2 meter height. So I have to pump that slab 1/2 meter. All right, so let's look at a typical slab of water. What is its volume?
So,
what is dV of a slab of water? Well, what's the area of that water?
1 times 2.
Okay. Times the density of the water. This isn't dV. Hold on. Let me write it like this. 1 times 2 times dx. That is the volume of each slab of water, each rectangular slab of water that we're going to lift out. You can actually picture it as lifting it over the edge of the aquarium. So the volume, or the force of that water, is going to be its volume times its density. So V, or excuse me, the force of the water is equal to its volume, which is 2dx, times its density, which is 1,000. So the force is 2,000 kilograms per meter cubed times dx. In other words, every single slab of that water weighs 2,000 kilograms per cubic meter times its thickness, which is dx. So the amount of work done is force times distance. So work equals from 0 to 1/2 the force times the distance that we have to lift it. Well, the first slab, that distance that we have to lift it is 1/2 minus x.
Okay.
In other words, if we think of lifting the first slab, the middle slab first, x is 0, right? And the final slab, x is 1/2. The final slab, there's no work required because it's already on the top. So there's no work required to push it over. So this should be the equation that's going to measure the entire work done lifting this variable force. Well, it's actually not a variable force. It's a constant force, but we're going to lift at a variable distance. This is a little bit of a different work problem than the rope and bucket. Notice that the rope and bucket problem was a variable force. As you did work, the force changed. This problem, as you do work, the force stays the same. The force of each micro slab of water is 2,000 kilograms per cubic meter, but we have to lift that slab a variable distance. The first slab we have to lift 1/2 meter. The next slab we have to lift is 1/2 meter minus how far up the aquarium we have to go. So I'm pretty sure this is the correct thing, and then that's relatively easy to solve. But the key distinction in this work problem, now I'm understanding it more. You can have a variable force or you can have a variable distance. When you're draining an aquarium tank, you have a variable distance and a constant force. When you're lifting a rope, you have a variable force and a constant distance. So those are kind of the two different situations you need to be able to handle. And these two problems address both of them.
Okay.
Okay? And I've got another one of these involving a conical tank that has olive oil in it instead of water. That's a similar problem, and we can look at that Friday morning perhaps as another work problem to look at.
Sure.
Okay?
Yeah.
Let's call it a session for today.
Sounds
And
good.
yeah, hopefully that's brought some clarification to things.
All right.
I will talk to you Friday morning at 9.
Yeah, sounds good.
Okay.
Are you
Have a good week, Dominic. Bye-bye.
Video?